If we really look at the time response of the system, when zeta is less than 1, I get some kind of a response which is shown in 2.18, the underdamped response of a second order system. So what we have is, we have a system where there is a steady state value, and then the system goes beyond the steady state value, which is called as overshoot. Then it slowly decays and comes within a tolerance band of the final value. So the time taken to go from 10% from 10% of the initial value to 90% of the final value is called as the rise time of the system. The peak time is the time required for the response to reach the peak of the first overshoot. Maximum overshoot is the measure of how much the response exceeds the final value following a step change. The percentage overshoot can be calculated by MP is equal to first peak value minus final value by final value into 100%. So it is equal to CTP minus C infinity by C infinity into 100%. Settling time. The settling time is the time required for the response to reach and stay within a specified tolerance band of its final value. The tolerance band is usually 2% to 5%. Decay ratio. The decay ratio is defined as the ratio of the amplitude of the first two successive peaks about the steady state value. Note that the response shown in figure 2.18 has the first overshoot of amplitude A and the second overshoot of amplitude B. Therefore, the decay ratio is B by A. Now, rise time. Consider the rise unit step response of a second order system. CFT is equal to 1 minus e raised to power minus zeta omega n t square root of 1 minus zeta square sine of omega dt plus phi. But phi is equal to tan inverse of square root of 1 minus zeta square by zeta. Let us assume that TR is the time required for the system to reach 100% for the first time. So what happens is CTR is equal to 1. So, but CTR is equal to 1 minus e raised to power minus zeta omega n TR square root of 1 minus zeta square sine of omega d TR plus phi, which particularly implies that e raised to power minus zeta omega n TR square root of 1 minus zeta square sine of omega d TR plus phi is equal to 0. Now, e raised to power minus zeta omega n TR by square root of 1 minus zeta square cannot be 0. So, sine of omega d TR plus phi is equal to 0, which particularly means that omega d TR plus phi should be equal to n pi. For the first peak, n is equal to 1, so TR is equal to pi minus phi by omega d, which is pi minus phi omega n into 1 minus zeta square. So TR at any time can be derived by pi minus phi omega n into square root of 1 minus zeta square. Peak time. The peak time is found by differentiating C of t and letting this derivative to be 0. So dC by dt at t is equal to Tp, which is equal to e raised to power minus zeta omega n Tp square root of 1 minus zeta square cos of omega d Tp plus phi into omega d minus sine of omega d Tp plus phi minus zeta omega n into square root of 1 minus zeta square e raised to power minus zeta omega n Tp. If you really solve this, you are going to get zeta omega n. So zeta sine of omega d Tp plus phi minus square root of 1 minus zeta square cos of omega dt p plus phi is equal to 0, but zeta is equal to cos phi and square root of 1 minus zeta square is equal to sin phi. So what you can do is, this particular thing implies that sine of omega d Tp plus phi minus phi is equal to 0, or sine of omega d Tp is equal to 0. This can happen when omega d Tp is equal to 0, pi, 2 pi, 3 pi and so on. Since the peak time corresponds to the first peak overshoot, we have omega d Tp is equal to pi. So Tp is equal to pi by omega d. We already know that omega d is equal to omega n into square root of 1 minus zeta square. So Tp is equal to pi by omega n into 1 minus zeta square. How you can find maximum or peak overshoot? Given the peak time, this is the value of C of t when t is equal to Tp. So Mp is equal to C of Tp minus 1. So Mp is equal to 1 minus e raised to power minus zeta omega n Tp square root of 1 minus zeta square sine of omega dt plus phi minus 1, which particularly means that e raised to power minus zeta omega n Tp square root of 1 minus zeta square sine of omega d pi by omega d plus phi. If you really simplify this, you are going to get mp is equal to e raised to power minus zeta pi by square root of 1 minus zeta square. If you want percentage overshoot, mp is equal to e raised to power minus zeta pi square root of 1 minus zeta square into 100%. Settling time. To evaluate the settling time, we must find the time for which CT reaches and stays within plus minus 2% for a 2% criteria or a plus minus 5% for a 5% criteria of the steady state value. Here it particularly means that e raised to power minus zeta omega and Ts by square root of 1 minus zeta square should be equal to 0.02, or e raised to power minus zeta omega and Ts is equal to 0.02 into 1 minus zeta square, taking log of both sides, minus zeta omega and Ts is equal to log of 0.02 square root of 1 minus zeta square. So Ts is equal to minus log of 0.02 into square root of 1 minus zeta square by zeta omega n. What happens is, as zeta varies from 0 to 0.9, this comes out to be 3.91 to 4.74. So Ts can be given approximately by the formula 4 by zeta omega n for a 2% tolerance. Similarly, settling time for a 5% tolerance is given by 3 by zeta omega n. So similarly, you have lots of problems in this kind of thing. So you can solve this. Next, we come to ramp response of second order systems. Here, R of t becomes t, so R of s becomes 1 by s square. So likewise, you can have C of s is equal to omega n square, s square plus 2 zeta omega n is s plus omega n square. And then you can divide it into partial fractions, a by s plus b by s square, c s minus s1, b s minus s2. You can solve for a, b, c and d and find out the corresponding responses. Likewise, you can find out response for delta greater than 1 and delta is equal and zeta equals to 1. And I leave this as an exercise for you.